So I'm going to talk about a whole bunch of work we've done in robot manipulation. So it's both going to include grasping and also some other things around active vision, prediction, and so on and so forth. At the end, I'm going to give a shout out for some work, a completely different line of work that I've done, which goes back to task planning and uncertainty and solves something called the open world planning problem. But I don't have time to talk about both, so I'm just going to talk about one in detail and then mention the other. So there's a whole bunch of people who actually did all the work, so thanks to them and the funders. Okay, so I'm going to talk about several things. I'm interested in frameworks for manipulation that both explain what humans do and also drive performance improvements in robots. If you think about what humans do, we know that humans, certainly in low-level sensory motor perception, perform Bayesian state estimation. Right? We know that from kind of classic papers like Cording and Wolpert from 2004. However, there are not a great number of results about whether or not we are decision theoretically optimal in any sense when we're making sensory motor decisions. So there are some papers, for example, around active gaze tasks, where you can say it looks like your eyes are kind of doing some kind of optimal Bayesian probing of a scene in order to detect features or make a classification. But an interesting question is to ask, when we're doing grasping, when we're doing manipulation, are we affected by uncertainty? Do we take account of uncertainty? And if we take account of uncertainty, how do we integrate it with other information that we have, and do we do so optimally? So we know from people like Christopoulos and Schrater that we do take account of uncertainty. So, for example, this is an experiment they did where they have an object, a robot moves it around a lot of times in front of you, and then your view is blocked, and you have to reach out and grasp it. And essentially, if you have no uncertainty, the finger tracks, because you track the fingers individually with little polyhemos or something like that, then they sort of go straight forward, and you can see that there are modifications. So basically, their paper was to show there are modifications of the path of your fingers if you start introducing uncertainty. So that's meant to be an ellipse of the uncertainty in the pose of the thing that you're trying to grasp. So that's at least evidence that we take account of uncertainty. However, that doesn't answer two questions. First of all, it doesn't say what other features are you integrating and are you sensitive to. And secondly, it doesn't say whether or not, when you're taking account of uncertainty, when you're reached to grasp, are you doing so optimally. So the experiment that we did is it's a cognitive judgment experiment. And what we do is we flash an object to you. So I'll show you again many times. And then you've got a choice of two grasps. So you take a two alternative forced choice paradigm. It's a classic paradigm in psychology. And here you can see that the object's elliptical. You wear 3D glasses, so you get some 3D perception, and then you pick one. And the question is, which one should you pick? And which of the two choices you should pick depends upon A, the uncertainty, and B, the shape of the object. And so the question we want to pose is, do humans take account of that optimally? And you can begin to show that they do, and there's a couple of steps to this. So first of all, what you can do is you have a round object, and you have an ellipse that essentially says how skewed the positional uncertainty is. So here, it's roughly distributed. The positional uncertainty is roughly is a circle. It's isometric. And then gradually we make it more and more elliptical. And if we're making it more and more elliptical, it's optimal to thus grasp from this side. I mean, assuming that the ellipse of uncertainty is much smaller than the range of which your fingers can go. So you want to grasp it from here, because over here you're not very robust, because it could be here or it could be here. And you can show, therefore, that the right thing to do is to be aligned with a major axis of the Gaussian. And the probability of that going up goes up as you become more and more elliptical. Whereas as the major and minor axis of uncertainty, as those become, the ratio becomes more extreme. So then what you can do is, however, then you can integrate it with shape. So now, for example, you can do this for not just one circular object, but for several different objects with different shapes. So that what you're doing is you're looking at the effect of the shape on the decision to grasp along the axis. In this case, we look at it in terms of the minor axis of the ellipse of the object, not of the major axis of the ellipse of the uncertainty. And so what happens is now you can start to do things like, for example, you can have an extreme positional uncertainty, but have it aligned with the major axis of the ellipse. And then you can switch it all the way around so that they're orthogonal. And essentially what's going to happen intuitively? Well, what happens intuitively is if you've got a kind of a pen or an ellipse-shaped like object, it's much more robust to this kind of uncertainty, if you're grasping from this direction, than it is to that kind of uncertainty. if it's orientated like that, right? So that you should see that in the decisions that you take. And you do see that in the decisions that you take, because essentially the more elliptical it becomes, the more you will be biased towards picking on the minor axis of the ellipse of the shape. So therefore, you like to pick up basically pen-shaped things across this minor axis here. And so you're biased, but you carry on all the way, that bias carries along all the way up. Well, the question, that doesn't tell us whether it's optimal or not, it just tells us the effect. So what we do instead is we look at the notion, we look at a model where basically what we do is we say, well, what would a rational actor do? So, for example, a rational actor would be able to say, for example, do a force closure analysis for the different positions in which the object might be, and then assess how many of those would be successful according to some force closure measure. And then decision theoretically, you ought to pick if you're not doing active information gathering, you're just deciding with respect to the current uncertainty, so it's a very crude measure of optimality, you would pick the one that gave you the highest success rate. And then what we also do is we have to optimize taking into account the fact that different people might have different biases as to what they perceive the mass or the frictional coefficients to be when they're making their grasping choices, because it's a cognitive task. So then what we do is we take, this is the data from the human. These different coloured lines mean different shapes of objects and different amounts of uncertainty, and this is what the model tells us. Now, in terms of fit between humans and psychophysical data, this is actually pretty good. It's when psychologists see this, they get reasonably happy. So this is quite a promising story, because it shows us that there is some evidence, at least, that humans are capable of being, in some sense, based decision theoretic optimal with respect to the current uncertainty, incorporating not just the positional uncertainty, but also modulating that with respect to the shape and doing so optimally. So that's we start out with a psychological result with a computational model. So that was the key finding. We choose between grasp actions approximately decision theoretically optimally. Decision theory. So we're just saying it's optimal. It's the one that's most likely to succeed. So the next thing, which I guess is the main really novel result of the talk, is about grasping novel objects. And here we're thinking about novel, primarily we think about in terms of shape. So the idea is, and we're interested in dexterous grasping, and we're interested in extremely data-efficient grasping. So, for example, we want to show one grasp of an object, like this cup, and we're going to demonstrate it to the robot. So we're going to guide the robot through, either in simulation or physically. And then we pick up the object, and then what we want to do is to present it with new objects, maybe drawn from the same category or maybe drawn from completely different categories. And we want, from that one trial, in one shot, to be able to adapt that grasp type, let's call it, to this new object. So on the fly, it will transfer it. So the key idea, and this is a theme that runs all the way through the talk, so it's an important theme for me to explain the motivation behind, is that in a lot of our work in our lab, we have used products of experts. And the reason we like products of experts in manipulation is because products are very good at generating compromised choices, of bringing together a group of experts and then probabilistically finding some choice upon which they can all, to some greater or lesser extent, agree. And if we think about those experts as being, for example, attached to some particular, say, finger link, as we're going to in a moment, and perhaps with a contact, in a sense what we're doing is, if we think about those contacts as representing as being kinematic constraints that we want to satisfy, what we're doing is essentially we're taking multiple experts about kinematic constraints and saying that we want to simultaneously satisfy all of those kinematic constraints. Some of these are going to be conditioned upon local information, so like local surface shape, and some are going to be conditioned on global information. Lots of people in grasping condition their grasps on global information about the shape of the object. We don't. And that has some advantages. It also probably has some disadvantages. But when we're talking about global, we're talking about the global hand shape. So let me describe the framework to you. The learning works as follows. What we're going to do is we're going to take an example grasp and we're going to learn two types of models, what we call contact models. These are mechanical contact models. They're kind of kinematic shape contact models. And we're going to learn these are the local ones, and we learn a global hand configuration model. And then we're going to, when we get to new objects, we're going to recombine these in order to find a new grasp. So what you do is we demonstrate the grasp, and then what we do is we extract contact points between the finger links and an object. An important part of or a useful part of our method is that we don't require prior CAD models of any kind. So this is data gathered from a Kinect sensor of a real object. You can see that it's incomplete. We have pretty good registration. And also, in fact, we don't have to extract, although we could extract, all of the contacts are extracted using forward kinematics. They're not extracted using touch sensing, although we have that capability. So having extracted those contacts, what do we do with them? Yeah?
Sorry, I just want to understand what's going on. So you have the point cloud.
Yeah.
And you have a robot. Is this physical?
It could be either a physical robot, which you physically guide, or it can be a 3D, it can be a simulation of the kinematics, which you can guide virtually.
I see. So a human is guiding it, demonstrating.
Yeah, absolutely.
And then when it makes the contacts, what is the model of the hand? Is that polyhedral model? Or is
yes, it's a polyhedral model. So it's a polyhedral model of each of the links.
Okay, so there's a number of contacts now.
Yes. Yeah. And what I've done there is through all of this, each one of these links will have a different colour for the points with which it's contacted. So the next thing that matters in building our model, so first of all I'm going to tell you how we build what we call the contact models. And we're going to have one contact model for every link in every finger. That could be the palm, for example, or it could be a phalange way down here, deep in the finger. It doesn't have to be just the fingertips. To do that, what we're going to do is we're going to represent, we have two key things, which is a representation of the object, which we're going to take from a point cloud, and we're going to turn it into a probability density. And a lot of the key for our methods to actually work is that we can turn everything into a probability density. Now, in order to have probability densities here, in addition, we need to have frames. And this depends upon, we're going to extract our frames dependent on a shape representation, of a representation of local shape. And essentially what we do is we are going to find a frame for every single point in this point cloud, or a subset that we wish to sample, such that one of these is going to give us the first principal curvature. One of these is derived from the second principal curvature, and then we test a cross product to get the normal. And that frame we're going to use to then locally encode a rigid body transformation for where the finger link is relative to that piece of local surface curvature. So that's a representational thing. And then, so this is a bit of the patch of the object. And then when we're going to learn our contact model, we need to know several things. We need to know how far away is the closest point on the finger. So this is the rigid finger link. This is a bit of the object point cloud. There's a point beyond which, I'll come back to that in a moment. We need to know how far, say for example, there's a little frame, which I've just shown you there. Here I only give you 2 axes, but obviously imagine 3. So we want to know what's the shortest distance from the origin of that frame to the rigid, to the link. And then we need to know the rigid body transformation to a fixed point on that link. So we have another frame defined on each link. And we can also think about this in terms of we need to know where things are in terms of the world as well. But in terms here, what we're going to do is in terms of our model, we're going to learn it's basically this rigid body transformation expressed in this frame here. We're also going to build up a model which is made of many of these rigid body transformations. So essentially what we're going to construct is a density over rigid body transformations. So that means I'm going to have lots and lots of frames here, each of which are all going to have a different rigid body transformation to this point. And then we're going to weight them by how far away this point on the surface of the object is from this from the nearest point on this rigid link. Sorry?
How do you get those points? You move the hand or what?
Those points are the points on the object. So these are just points in the point cloud.
So how do you select them?
We select them according to how far they are away from the finger link. So if they are beyond a certain distance from the finger link, we ignore them. And then what?
How far the finger is from the object?
The finger link
Yes.
could be maybe a few millimeters or portion of a centimeter away from a certain patch on the object.
Yes.
And we would still include it in our model. If it's further, then we won't include it. But equally importantly, what we're going to do is we're going to have one kernel, one Gaussian kernel for each of these rigid body transformations. And then we're going to weight those kernels, and we're going to weight them with an exponentially decaying weight, where what happens is the further you move away, the quicker it falls off. And then we just have an absolute cutoff at some distance delta. So the consequence of this is that we get so if we're going to extract all the connections to all these links, and there are going to be many of these, because say, for example, we look at this link here, it's actually very close, perhaps it's not in contact, but it's very in close contact to the object at many points. And so we have many little rigid body transformations which say how that link is related to those frames of reference. And then we're going to do that for each of the links. So here there are 4 involved, but it could be more. And the kinds of, if we look at, say, a different link in each of these, say, for example, in this graph, the same graph, 2 different links, what we can do is we can take this, this kernel density model, and it's a kernel density model in 7 dimensions. No, 9 dimensions, because we've got 9, because we've got 7 for the rigid body transformation, and then we have 2 for these are the principal curvatures that we talked about. So we're also going to include the principal curvatures as a way of saying, well, what kind of curvature does it like? And what I've done here is I've marginalized down everything out except the density over the curvatures.
Curvatures are, you have a compliant finger or
No.
rigid? You have a rigid contact.
Yeah.
And you have a rigid object.
Yes.
So where does the curvature comes from?
The curvature comes from the object.
Well, it can't, because if I touch rigidly, then I just have a tangent, which is plane, or normal, which is plane. It's not curvature, unless you have a compliant finger or compliant object.
Okay, I think we're thinking at cross purposes here. I think I'm explaining myself badly, because I think you're thinking about something else. It's definitely not compliant. If I have a surface, if I have an object surface, and I represent that with a point cloud, I can calculate the principal curvatures, and I said I use that to define a frame.
You can compute the principal curvature if the surfaces are curved.
Are curved, absolutely correct. So an interesting thing, and it's a very good point. If you have a flat surface, then the principal curvatures are indeterminate. In which case, what we do is we sample a random set of frames, because since it's undetermined, we can take any one of a number. So we take a whole bunch of those in that case. So you're right. And that if it's yes.
In a contact, you have really only since in your setup, in your agent setup, you don't need curvature. You just have a point tangent.
You're right. In some sense, you don't need curvature,
right.
But actually you benefit from having curvature.
It helps you if you are moving.
It also helps you because what you're getting is you're getting information not just from the single contact point, but from the points around it that tell you about the local shape. So I think the way I think about it as a physical metaphor is to say it's as if the local curvature that this patch contains lots of information, and there's little strings that anchor it here. I mean, that's just a metaphor, but I think it's quite a good one.
I'm sorry to interrupt.
No, they're good questions, and they help with the exposition.
A small audience.
Might as well take the advantage. So what I've done here is I've marged to show you the difference for different finger links from the same grasp in terms of these kernel density models. What I've done is I've marginalized away the portions of the distribution which relate to the rigid body transformation, and I've pushed them down onto the sizes of the principal curvatures. So obviously the magnitude of the principal curvature tells me how curved the surface is in one direction or in the other direction. And so what happens is when my finger is further down, obviously I still have principal curvature in one direction, but in the other direction it's largely flat, hence they kind of bunch up on this axis here. And here, because it's on the corner, it's curved in several dimensions, and so you can sort of think about it in a different way. So we have these models, each of which is very different for each finger link, just from this single grasp. And this is what we call a contact model. And we learn one of these for this grasp for every finger link that's in contact. So if there were 1, 2, 3, 4, maybe 5 bits of finger link that were in contact here, we would have 5 of these models. If the finger links are further away, such as these ones, we would not learn models for them. And then we also learn something called a hand configuration model, which is very difficult to visualize. So in a sense, probably ignore what's up there and imagine that, say, for example, I do a pinch grasp, I have one hand shape. And as I'm coming in, I'm exploiting I have a little manifold in the configuration space of the hand. If I'm doing a power grasp, I get a very different hand shape. And so that's the global information that we remember, but it's global information about the hand shape, not the object shape. Now we've got two types of models, of which we have one instance in one case and a variable number of instances in the first case. And now what we're going to do is we're going to do inference. Now we're going to show a new object, and we're going to infer a grasp for this object based on this learned model. So what we're going to do is we've got our contact models, of which we might have many. And first of all, for each one of these, we're going to have that contact model, and we're also going to have a new object. And of that new object, we have a new point cloud. And as I said, we represent our point clouds as densities. So we're going to turn this into a density. This is a density here. And then what we're going to do is we're going to convolve the two densities. And essentially the result of this is going to be a probability density, or a set of samples from it, in fact, that allow us to say, in a memory-based way, to reproduce the original relationship with local surface curvature. Where would, in a sense, this finger link like to be on the new object? So what happens is that, say, for example, we take this grasp, which we call pinch with support, and we take this finger link, and then we take this new object here with a point cloud, again, partial, and we treat these two as densities, as I've already said, and then we convolve, this is the contact model I'm convolving, obviously not the density of the object, it's the contact model density together with this object density. And what we will do is we will recover a new density in a sample-based way of where this finger link would like to be on this new object. And then we can do this for every single contact model. So what we're saying is we're saying for each of the finger links, where would it like to be on the new object? And then what we're going to do is we're going to combine those models in a product of experts, and we're going to hill climb to try to produce a grasp configuration on the new object that is as likely as possible, according to the product of experts, where each of the experts was learned from a single grasp, the same grasp, on some other object.
This is your generalization.
This is the generalization. So if we look at different finger links, and then we convolve them, their contact models together with the query, with this query objects model. This is a different density. This is the one I just showed you, and this shows you again the way that they vary. So some of them are much more liberal about where they would like to be, and some of them are much tighter. Then what we do is we've got our new object. So we're going to do a simulated annealing procedure. But first of all, we need to randomly start in a place. So what we do is we sample a hand link, and then we sample from its query density. And then what we do is we sample our hand from the hand configuration model. And this is neat because by forward kinematics, it now produces a complete solution. So it massively cuts down the search space. And then basically what we do is we then randomly perturb and do simulated annealing in the configuration space, judging the quality of the model as being the product of the quality according to each of the experts. And so what we're doing is we're randomly perturbing, we're evaluating the likelihood, and we're retaining the improving perturbation. So these are actually pictures which show the result of the final process of these random perturbations. So these aren't intermediate steps; these are the final cases. And the consequence of this is, because what you do is you do this. You start, you sample a finger link position, you sample a whole hand shape, you then simulate an anneal. And then you just do it again. But maybe now you sample a different finger link. So maybe this time I do this one instead, or I maybe even do one inside near the palm. So that what happens is that each time I'm starting in a different place, and then I'm simulated annealing, which will carry to some local optimum, essentially. And so what we're ending up with is quite different grasps on the object. Although here, all of them, because of the grasp we're adapting, all like to end up on the handle, but they end up on the handle in different places. There will be other grasps as well. This is the representation of the product of experts, very simple. So this is the density according to what we call this contact query density, which was the result of the convolution between the contact density and the object model density. And then this is the probability the likelihood according to the hand configuration model. So we're just multiplying all these together, and we're just taking the argmax just says, well, we're just taking the one that's best. Yeah. There's no weighting on the links.
Okay. And you don't look at interactions between links. In other words, there's sort of the idea of antimodality that you want to have opposite forces. Right now, you're not considering.
Yeah, there's nothing. So.
Speak up a little bit louder.
He's not looking at the force relationship between the two links. He's saying, as I understand, if I have it right, you're sort of figuring out where does that finger want to be.
Yeah.
And then
he doesn't have a Jacobian of the hand to begin with.
Yeah.
So he doesn't have the geometry.
Well, I think that comes in the hand configuration.
Yeah.
Because as soon as you find one link, it sort of then because you have these hand configurations, it sort of tells you where the other links would end up.
Yeah.
Right?
Yeah.
And then you're checking how happy how sort of what is the quality of each of the other links.
Yeah.
That are around there, and then you're summing, you're multiplying all those.
Yes. Except there's one. So now it's worth making this point, having explained all of that sort of the mechanics, which is that these densities don't tell us anything, obviously, about the quality. About the quality of the grasp. They don't tell us anything about. There's no force closure here. There's none of that, right? It's all it's doing is it's basically just it's purely memory based, but it's factored and it's probabilistic, so it's generative, and so it's a very, very particular way of doing this that has no guarantees about whether or not this will work. There's no notion that it will work, but so think about it as memory-based grasping. Sorry, you wanted to ask a question,
I
right?
just wanted to say that in your generalization step, what's missing is dynamics.
Absolutely.
Because you had that ball, I was just thinking, and you wanted to transfer it to the kettle. Well, if the kettle has a water, it won't be able to do the same grasp as it generalized.
Yeah.
So yes, that's very, very. Look, we are making little steps.
Absolutely.
Yeah.
So it's very simple. Let's put it like that.
Yes.
But the performance relative to where we expected it to be is not a little step. So let me show you some of the grasps, because there are several nice features of this method. Because what we're going to do is we're going to rank them by their likelihood, and then we're going to pick the most likely one. And we can do this many times. And here, in fact, what we do is we pick many of them to show you the variety of grasps that we'll get on this object. So we're going to get, actually not on this one, we're going to see it in a moment. And what we did, so when we were training, here we just trained on 5 grasps, 2 on this object, 1 here, and 1 here. And then we show about sort of 40 or 50 test objects. We have no models of any of the test objects. So one of the nice features of this is that we don't need a CAD model in order to grasp, because we're not making any assumptions about force closure. So these are the 5 example grasps. So you can see there's 1 power and 1 pinch on this object. This we call pinch with support. We've got a mug handle grasp and a power grasp on a box. And now what we're going to see is now we take the new object. And here, initially, what we're going to do is we're going to take 7 views of the object with a depth camera in order to get a pretty good point cloud. And then these are some of the sample grasps that we get. And what's happening is we merge grasps from all the different 5 trained models. So what happens is we do the optimization. It's saying you're going to do grasp type 1 or grasp type 2 or grasp type 3. We run this process for all of them, and then we interleave them in a ranking, and we just pick the top one. So it's also selecting the grasp type. To do that, we have to do a normalization step to take account of the fact that some grasps are less likely because they involve more links. What you just saw is that it works rather well as a side effect from partial data. So if you take an object and you just take a point cloud from one view with a depth camera, you end up getting very, very little data back off the object. And then it's deciding which grasp do I want to perform on this object. And from that partial point cloud with maybe less than often 20% of coverage of the surface, it's able to identify and execute a dexterous grasp, including quite sophisticated grasps such as the handle grasp, where you're also got that. Sometimes you're able to get the finger in the bracing position, not always. So it's robust to partial data. It's also, so we don't need any models. It's robust to partial data. It's also robust to radical pose changes. Sometimes that involves changing the grasp. Sometimes it involves just using the same grasp but deploying it in a different way. So we're able to grasp objects that we've never seen before, where we've got one shot for each grasp type, do it partial data. So although it is a very simple algorithm in some ways, and it doesn't make any account of dynamics, it does work. We were very surprised about how often this works, and often that's a clue something's going nicely. So if you just saw there, that grasp was adapted from the tube into the glass. So we're getting quite radical generalization with some grasps, whereas obviously the handle grasp, it tends to only be used when we've got handles. So here's another example of transfer. So this is the power grasp on the box, and we can turn it into a power grasp on a Coca-Cola bottle or another box. So the neatness of this method is it's extremely data efficient, and yet you're getting quite strong generalization. The weakness of the method is that it doesn't take account of dynamics, it doesn't give you any guarantees about performance, and it works, if you've got 7 views, the original method works with about 85% of the time, and if you just take a single view, it works just a bit, it's about 77% of the time. So there's still plenty to do. But these were grasps that were shown that were adapted from a bowl, so you can see, again, we're getting very radical generalization.
800,000 training samples.
No. We have 5. And I think that's a nice...
I had a talk here recently about 800,000 training samples.
Yeah. And I think data-rich learning or data-expensive learning has a place. I think also data-efficient learning has a place.
Guys are telling me that it took them 2 months. Did you hear that?
Who are you thinking of?
This is Sergey.
Oh, Sergey. Oh, yeah. The Google experiment.
Yeah.
I know the paper. I know the paper. So this is right at the opposite end, in a sense, right? We're trying to get as much from 5 samples as we can, and doing dexterous grasping. So that's the main. I think that's the main thing that I'm trying to advertise. But there's variations. We've also got this to work with underactuated hands, although we haven't done as much with it as we would like yet. So it basically we can adapt the method. We need a small change to the method in terms of the fact that we have to think about where was the hand when it began the reach to grasp. We actually remember the reach to grasp trajectory as well. And we remember reach to grasp positions that get us close to the kinds of contacts that we want, but we have no guarantee that we'll reproduce the similar contacts on the new object. But it's neat to see that it works on a whole variety of different hands. So we've tried it on shunk hands, we've tried it on dexterous fully actuated hands, dexterous partially actuated hands, all of these. What we want to do next, and we've got some of the data to help us do it, is to now take advantage of the fact that sometimes when you're grasping something, you actually exploit contact with the environment. So when you come down and you pick something thin off the table, like a mobile phone or something, you actually exploit the contacts, and then you want to take account of, as it were, the changing contacts. So actually now what we do is the idea is we learn a sequence of these contact changes. Now that means that we'd have to have a slightly more simple contact model, but we think that it's possible to do this. So we gather the data, and that's one of the things we would like to do. We can also turn the method from a picking method into a placement method. So here what we wanted to do is we wanted to sort of train it how to put things into a dishwasher rack. And then we're going to give it novel plates, so plates it's never seen. It's just doing it with plates at the moment, but the plates are all subtly different, and the tolerances here are really, really small. And now you can think of the dishwasher rack as being the hand. So this is what we're trying. We're trying to find a trajectory to place it in such that the changing contact relations as it comes into the dishwasher rack satisfy the original models. So we learn by placing it into the dishwasher rack, and then we'll show it new versions, new plates, and then we have to figure out how to get those into the dishwasher rack. And so we can think about this notion of contact learning, not just for doing grasping, but much, much more generally. We've also been doing a lot of work on active vision for grasping, and this goes back to the decision theoretic stuff. So this is a little shot from a paper by Mary Hayhoe and Mike Land, where someone's making a peanut butter and jelly sandwich. I suppose in England we call it a peanut butter and jam sandwich, but I'm here, so it's definitely a peanut butter and jelly sandwich. And then we do have peanut butter, but weirdly, we do have Marmite as well, but you either love it or you hate it. The weird thing is I hate peanut butter.
Every Brit I've ever met hates peanut butter. That's
really?
Yeah.
Oh, okay. No, my sister really likes it, but anyway, okay. Anyway, so peanut butter and jelly is the sandwich being made, and this is the sequence of gaze shifts. I mean, you can't clearly see what the sequence is, but the result that comes out from the literature again and again is that you look at the thing that you're about to manipulate or the place that you're going to go just before you manipulate it. So an interesting question with gaze fixation is what could drive that. Now, Dana Ballard and Nathan Sprague came up with a model some years ago that it basically explained if you thought about having different behaviours. And then those different behaviours had a walking agent called Walter, and then it wasn't doing its gaze shift, but what it was doing was a kind of mental visual attention about what to process in the scene from an image that was always wherever it was, it could either walk this way or turn this way, and so it always had a fixed picture. So it wasn't doing gaze shifts, but what it was doing is it was deciding what to process from the image. We adapted that model, and we show that the model can be used to explain when you've got not multiple behaviours but multiple motor systems, and you are doing gaze shifts. So we can use it to explain gazes in manipulation. And the basic idea is that active vision is a kind of a reward maximisation problem, And what happens is the eyes get rewards as a thank you from the hands for helping them do better on the task. So the size of the rewards that the eyes get is exactly the size of the additional expected reward that the hands will get. And so we started off doing this in simulation. So this was a little simulation from the iCub. And what it's going to do is it's going to do gaze shift. So here we assumed that the manipulation problem was solved using magic Harry Potter hands, as you do in simulation. But the point was you had to have your hands over the object in order to be able to manipulate them. So there was some uncertainty there. But the point was that the gaze shifts always precede, as you would hope that they would, the place. So we were also uncertain about where the boxes were, the trays were that you had to drop the objects. And so it was always looking to reduce the task-relevant uncertainty. We then applied this to explaining human data during manipulation. So here what happens is this is an experiment from Johansson from 2001, where you reach down, you pick up a bar, you move the bar around an obstacle, hit a target switch, bring it back around the obstacle and put it back down in the original place. And the colours here show the sequence of gazes, roughly, that the humans make during this task, and they're presented here. So your grasp sight zones, into the obstacle, target zone, and so on and so forth. This is the sequence that we get. It spends a lot longer looking at the obstacle, but the sequence is right. Now, this is the model that uses reward and uncertainty. I haven't given you the maths of it, but if you just look using uncertainty, if you're not task-driven, you get a completely different pattern of gazing. So this is a good account. It's not certainly the only account. There are other competing models that I can imagine or that we've tested, but this was the one that does the best. So it provides a decision theoretic account that matches some of the limited human data that we have. Then we want to take those ideas of task-driven vision, and we're going to use them now not in a strictly decision theoretic way, but we're going to use them in a slightly more heuristic way to do grasp-driven vision. So we take our grasping algorithm that I've shown you, and what happens often, if you've only got one view and you're doing a grasp, sometimes it goes wrong. So you don't get quite enough surface information around here to embed the grasp nicely around the object. Whereas if you take just a few more views, then you do better. That's not surprising. So if you don't want to do 7 views because it takes you quite a while, but you don't want to do 1 view sometimes because it doesn't give you very much information. So what you maybe want to do is 2 or 3 views and then try to get the best that try to get some good trade-off. And the question is, if you've only got 2 or 3 views as a budget to spend, which views should you have? Well, here we didn't quite do it in a decision theoretic way, although we think that we can. But instead what we've been doing is we have a method whereby we try to imagine where the fingers want to be on the object and then trying to recover as much information as we can about the patches of surface near the contact points. Actually, I'm going to skip on from this bit and show you this bit. So this explains it quite nicely. If I've looked from this side and my hand has decided to go here, but it hasn't got a lot of information either around this corner or on the back side of the object, which could be thicker than it supposes because it's looked from this direction over here, what we do is it works out that the best place to look is to look from the other side and fill in that information. Coincidentally, it will then fill in a lot of other information about the object, and that may in fact cause it to replan its grasp, to move it to another part of the object. That's fine. But the point is that the vision is being driven by the sites where your fingers want to go. So it's not decision theoretic in quite the way that I showed in the previous video, but it is at least driven by the grasp that you think that you want to execute. And then we look for safety and we look for finding the grasp. So we also, if we have other things in the scene, we have an Octree representation, and what we try to do is we try to find out enough information about the bits of the Octree that might mess up the trajectory that we plan in to now actually execute the grasp. In other words, we might bump into other things along the way, and we want to minimize the chance of that, so we do then some active vision to help us with that. And then we can then apply this method to, for example, now grasping up cluttered scenes with novel objects. So what we're doing is we're looking around, and we're looking around in order to be able to identify information about where it wants to grasp right now, which can change, and also information about occluding about objects that it might bump into as it's going to lower its hand into position to grasp. And all of these objects are novel objects to it, and they're very closely packed. So although it's not as challenging as many scenes, the hand's extremely fragile, so we can't have any unexpected collisions at all. So that's combining the active vision work with the grasp learning work. We've also been trying to do this with touch. Doing it with active touch is extremely difficult, and the reason being that if you're a decision theorist like I am and you try to think about it as a POMDP, you go insane very quickly, because POMDPs, where the underlying state space is of finite dimension, it's not a finite states, every finite state that you add an extra continuous dimension to the belief space. If you have even one continuous physical dimension, you have an infinite dimensional belief space, and you don't want to plan in that. So what we do instead is we embed a measure of the information that you can get into the physical space. Essentially, what we're doing is we're warping distances so that routes for the hand as it's reaching towards this object, that it's not quite sure where it is, routes that will gather more information about where the object really is, the distances along those are shorter. So it's like turning a Euclidean space into a non-Euclidean space. And that method allows us to do this kind of touching, and then when we touch, we update our belief distribution about where the object is. So here we have to have a complete model of the object in order to localize it. Okay, bye Ken, you've got to go. See you. No, it's all right. And then so then what we're doing is we're coming down, we're touching, and then we're updating the belief, and then we are then replanning a new grasp, but again taking into account the information that we might gather on the way. Again, not decision theoretic, it's a heuristic, but it works more effectively because we're, in terms of computation, we're using much less computation, but we're still achieving some improvement in performance. And the final thing I want to talk about is prediction. So one of the things, and this was actually the stuff that we started out with, which is that when we're doing prediction, we know from humans that we do prediction and manipulation. So this is a result from Wing and Flanagan from the 1990s, where they showed that when you're doing something like you pick up an object and you accelerate it against gravity, obviously by definition it gets heavier. And you would ask a question about what happens to the grip force, because the load force is going up, and then when I drop it, it's going back down again, right? And it's actually going below the sort of nominal static weight of the object. So what happens to your grip force? Well, in fact, your grip force goes up in perfect harmony with the load force. And that's as far as that. So Wing and Flanagan said that this is evidence for the fact that you must be doing some kind of feed-forward control. That essentially what's happening is you're using an efferent copy of your arm command, so you know how fast you're going to accelerate it away from the Earth or towards the Earth. And then what you're doing is you're using the efferent copy to index a controller that tells your gripper how hard to grip. And you can modulate your grip then very, very precisely in time with your arm. So that's evidence for forward models, and there's other sort of evidence. And there's a nice quote from Flanagan about how he thinks that prediction is really at the heart of the manipulative skill of humans. And so we started about 10 years ago now to think about prediction. So if you talk to sports people, for example, they say, if you talk to David Beckham, he'll say that when he kicks the ball, just as his foot is touching it, he knows where it's going to go. He knows that where it's going to go in the goal. So elite sports people are very, very good at doing these prediction tasks. And this is a rather nice little video of a crow called Betty. And Betty was a subject in Alex Kochelnik's lab in the late 1990s in Oxford in the Animal Behaviour Lab. And she was given wire. She had experiences in nature with twigs, and she'd seen wire before, but not really to manipulate it. And then she was given this problem. She had the straight wire, and what she was doing was basically coming down, trying to kind of hoover it, sort of lever it up. And then instead, when she realised this doesn't work, she sticks it into a crack here, makes a hook by bending it round, and then goes back and hooks it up. What the video doesn't show you is that her male mate, Abel, then flies in, nicks the food, and flies off with it. So it seems like a fairly stereotypical gender relationship there. So that it's tempting to think that Betty's doing prediction as well. Now, I'm not suggesting that David Beckham and Betty have similar cognitive levels of skill, but even so. So, forward models of objects. So one of the things that we started out by doing was we started out saying, well, is it possible that I don't know if even these movies are going to play, actually, but let's see if no, they're not going to play. So what we started was, we started off using physics engines. And we started off trying to figure out models of the objects by identifying the frictional coefficients and various other properties. And we had some limited success. And what we did is we used this in papers sort of about 2010, 2011 to show that so physics in vision is very popular at the moment. We were sort of trying to do this about sort of 8-9 years ago, and we learned two lessons. First of all, you can get it to work. So, for example, what happens here is that the robot pushes the object, it flips over behind a distractor, and if you don't have a physics engine guiding your forward model for your tracker just loses track completely. Whereas if you have the physics engine and you've learned the parameters of the object, it works. But the problem is that if you let the physics engine run free, in terms of the learning, the model identification, it starts doing very strange things. Like if you let it adjust gravity, it will change G. It will tell you that two objects that you know have the same mass have very, very different masses. It will do all kinds of strange things. And in addition, physics engines don't always make very good predictions. So what we thought was, rather than doing physics engines, we'd try to learn models of the objects. And I should finish up now. So I'm going to skip past some of the slides and just try to get to the headline, which is that what we tried to do was, rather than learning a general physics engine, using a learning method, which I think is something that people are trying now, what we did instead was we did it in a modular way. So we said, rather than learn one physics engine, learn many. Just learn one for each different object. So each one is very, very stupid, but it knows a lot about one thing and one type of interaction. So, for example, you might have a little learned model for this object or for this object. And then what you do is when you see the object, you see what it is, and you select which module is the right predictor, and then the predictions are made by feeding over many steps, by feeding the predictions back into themselves and coming up with a prediction that says, in a few seconds, after many moments of pushing, and I know how I'm going to push, so I know the sequence of actions that I'm going to take, and I know where I start, I want to predict where I'm going to finish, and all of the places in between. And I want these predictions not to be qualitative, I want them to be metric and precise. And so that's what we set about doing. And again, we use this notion of kernel density machines. And so we did this kind of what we call modular learning. So now what we're doing is we're learning predictors, and we learn them using regression. So we use these kinds of regression methods like locally weighted projection regression. And we also tried it with kernel density machines. And the headline, the take-home, is that the kernel density machines tend to do better. The regression machines can do quite well in some circumstances, but they don't always work. But another nice feature of it, and so these are incidentally, the yellow here, the green here, is the prediction that's made with no feedback from perception over the whole time series. So in other words, what you're doing is you're feeding back the prediction and making a complete prediction ever before you move. And if you look at it, we also gave the same data to tune the physics engine. So we took a physics engine like NVIDIA. And then this is an example of where the physics engine fails. So, for example, what happens is that the physics engine, even when you've tuned it on the same data, so you've given it the same machine learning opportunities in a sense that the basic sort of pure machine learners have, it often or sometimes gets it badly wrong. We can also show that we do this. This is learned from simulated data, not real data, but we can show that it works. So now it learns what the peculiarities of the physics simulator are, but it also works if the object's basically sitting on a non-planar surface. So we wanted to show some ability to take account of context. But this means you would need to learn one of these models, not just for every object, but for every combination of objects. So it's very intensive in terms of memory. But if you look at the performance of the kinds of systems, these learning systems tend to do much better than the physics engine in terms of predicting where the object's going to go, but they sometimes violate physical principles. So there's a whole bunch of different problems that we tried. We tried different. I'm going to skip to the end. One of the neat things at the end is that it turns out there is something that you can do with the physics, which is these learned models, because they're basically made up of lots of little Gaussians over rigid body transformations. Very much like I showed you in the grasping work, these Gaussians will predict physically implausible things, such as that the finger can go inside the object, which is obviously nonsense. And physics engines are made up of two parts. They're made up of a dynamics engine, and they've also got a collision checker. And actually, the collision checker very nicely and compactly encapsulates all of the kinematic constraints that you have when you're manipulating rigid objects. So a neat trick is to sort of turbocharge this method or add a little bit of performance, a small step, in terms by what you do is you optimize the predictions of the learner to fit with at least the rules that the collision checker tells you must be adhered to. And this allows you to stop making predictions like this, where the finger's inside the red object, and optimize them so that you then get the green prediction rather than the red prediction here.
How many iterations you have?
In what sense? In learning. So, I mean, how much data do we need?
Huh?
Do you mean how much data do we need?
Data, yeah.
So we were able to learn.
Repetition of your experiment.
We were doing about up to 900 pushes of an object.
How many?
900. But we were able to show that it was outperforming the physics engine in terms of the gross position of the object after about 10 pushes. So It doesn't do very well, and it's often gives you physically implausible predictions. But again, it's relatively data efficient because we're using kernels, and they perform relatively well in terms of their data efficiency. But this is just a trick we can play at the end that allows us to do a little bit better, and we can show that in the graphs. And that's where I'm going to finish, except that I'm going to just while we're closing up, I do a whole bunch of other work, and I didn't have time to talk about it, where we're interested in planning in mobile robots using classical planning techniques. And there's a very old problem which has been around since the shaky system of 1975, which is called the open world planning problem, which is when you're planning in a task planner, how do you take account of the fact that new things might pop up that are not in your world model? And what we were able to do is we were able to solve this problem in a separate piece of work. So the grasping work that I've showed you is published in IJRR. It came out in 2016 in July. The pushing work came out in Autonomous Robots in 2016, but we've been published papers back as far as 2009. So there's a whole raft of work. It was very difficult to get the final paper accepted. A lot of people thought it was bad work, but it wasn't. But it got there in the end. And then this work, which is not the subject of this talk at all, but it's just a shout out. This work is published in Artificial Intelligence Journal and also it's not even out in print yet, but it's been out online for about a year. And this is work I'm also very personally proud of. I think it's an interesting thing. So if you're interested in robot task planning rather than manipulation, that's something else you can go and look at. And I'm done. And I'm sorry I was a little bit over time.